So a couple of reminders here, guys, before we start. Okay, the Unit 4 exam will be next Wednesday, okay, so a week from today. And the review package for that will post on Friday morning, so you can have a look at it over the weekend. And then obviously our final exam is January 23rd at 9 a.m. Okay, I'll have to see if I get a chance today to look up. I don't think they've posted which room it is in yet, but I will have a look. So just make sure that you're going over things, pop in to see me for help if you have questions, because remember, we're not going to get really any in-class time for final exam review. Okay, but the stuff I posted yesterday on Google Classroom should be helpful for you. There's also a review package along with the videos for a review for chemistry, biology, and physics. Okay. All right, today, kind of a long lesson. We're going to be going over a lot of things in this lesson, all of it about energy transfers. But unlike in the physics unit where we talked about mechanical energy transfers, this is going to be thermal energy transfers. Okay, so we're going to be looking at a lot of new terms, okay, and how they apply to a lot of kind of very common things in real life. Now, apply is the key word here. Everything in this lesson, when it appears on the test, is going to be an application type of question, okay, where you can show me how you can apply your knowledge of what we learned today to a practical situation. All right, so you need to kind of be listening and taking notes on that from that perspective. Okay, I'll talk about some places where these things apply. Okay, those would be good things to write down. Okay. All right, so we're going to look at the three parts of the Earth. Okay, that would be like multiple choice stuff. It's pretty straightforward. Okay, understand how energy on Earth is absorbed, used, and reflected. Those are, guys, what I call the big three. Okay, this whole unit is, or this whole lesson is threes. Everything is in threes. Okay, so when light strikes the Earth's surface, three things can happen to it. It could be absorbed. It could be used. Sometimes we also say converted. Okay, and it could be reflected. All right, those are the three fates of light when it strikes the Earth's surface. Okay, what's the only thing on Earth that can actually convert sunlight into something else that is not artificial? Plants. Okay, we are talking strictly about natural ecosystems, processes, that kind of thing. Okay, yes, certainly solar panels can turn, solar energy directly into electricity. They are not natural. We are talking about the natural things when we talk about the fates of light. Okay, so converted, okay, by plants into chemical energy. Yes, true. Also converted by solar panels into electrical energy. Yes, that would be true. Okay, so absorbed means energy comes in and probably the temperature is going to go up. If you absorb energy, then your energy has to go up, or the Earth's energy in this case has to go up. If it just reflects off, does it change the energy at all? Okay, and then understand how the Earth and how the energy and the Earth interact to produce the conditions necessary to support life. Okay, so we'll quickly that's going to be kind of an overarching theme through the whole thing. Okay, so the three parts of the Earth that we're going to be concerned with are the atmosphere, the lithosphere, and the hydrosphere. Okay? The atmosphere is all of the gases surrounding the Earth. The lithosphere is all of the rocky parts of the Earth. Okay, so basically like its surface. Okay, and the hydrosphere is all of the water on or under the Earth's surface. Some water is trapped under the Earth's surface. Okay, so we'll start with the atmosphere. The atmosphere, in terms of energy transfers, is by far the most important of the three. Again, we're back to three again. Okay, atmosphere, lithosphere, hydrosphere. Okay, the atmosphere is the most important because it's the most mobile. It can transfer energy because gases can move freely. Okay? When the Earth's crust moves, generally that's bad. Okay, what do we call that? An earthquake. They're generally not good. Okay, lots of destruction and death. It isn't a good thing. Okay, so the Earth's surface doesn't move very much, which means it doesn't really have a lot of ability to help transfer energy from one place to another. What part of the Earth gets the most solar energy? The equator. Okay? Is there going to be a natural process that's going to try and move energy from the equator to the poles? Okay, because of what law of thermodynamics? Second law. Okay, it all kind of comes back together. Remember how I said this unit is a hodgepodge of the other three units? Okay, we talked about those laws of thermodynamics back in physics. Here's where they kind of apply. Okay, so the Earth's atmosphere is the most mobile because it's a gas, or it's full of gases. Okay, and so it can move really, really easily. The hydrosphere would be the second most important, okay, because it's a fluid still. Okay, the oceans can move, they can also hold lots of energy. Okay, they're all part of the water cycle. Okay, all of that's important. The Earth's surface, because it can't move, it can really absorb energy, but it can't really transfer it anywhere. Okay? It's hard to transfer energy through a solid material over long distances. All right, so the atmosphere is the layers of gases that surround the Earth. Okay, the part that we live in is called the troposphere. Okay, so that's where the air is the most dense. Okay, where the most oxygen is present. Okay, all of that kind of stuff. All right, above that is the stratosphere. Okay, now basically all life exists in the troposphere. After that, life doesn't exist. Okay, are there some places on Earth's surface that you can stand that would be outside of the troposphere? Yeah, the tops of the tallest peaks in the world. What do we call the area on the tops of those mountains? Somebody whispered it. Okay, summit, yes. I was thinking of another word that's quite a bit darker than that. It's actually two words.
I almost said depth point, but I don't think
It's the first word is depth, yes. The death zone. Okay, we call the tops of those mountains the death zone because living organisms cannot survive for very long in those conditions. The air is too thin. Okay, because the air is very thin, the pressure of the air is also very low. Your body evolved to be in surface of the Earth kinds of atmospheric pressure. Okay, if you go above that, or if you go deep down in the ocean, the balance of that pressure doesn't work anymore. So if you're standing above, okay, or in the death zone, you can only live there for a couple of days tops because your body just starts to break down. Okay? There isn't enough pressure to keep the fluids in your body fluid. Okay? They want to evaporate essentially. They want to come out. Okay? That's why you can get fluid in your lungs. You can get pulmonary edema, which basically means you drown in the water that starts to form in your lungs. Okay? It's like having pneumonia, okay? Except it's caused by a high altitude instead of an infection. There's very little oxygen. Oxygen is necessary for your cellular respiration to occur. The low levels of oxygen at that altitude don't let that occur very well, and your body starts to break down. Okay? Basically, you need to get to the summit and back down out of the death zone, okay, as quickly as possible. Right? If you don't, you will end up like many of the unfortunate souls who litter the summit areas of many of those mountains. Okay? Oh, it's dark. I mean, it's hard. It's hard work to be up there, right? There's so little oxygen. The pressure is very low. Okay? You see people who are, well-tuned athletes, let's say. Okay? The people who are going to climb Mount Everest effectively are going to be in incredibly good shape. Could probably easily run a marathon at sea level. Okay? But up there, they take one step, and it's like they've sprinted 200 meters as fast as they could. Okay? They take one step, and they're just... and they have to stop, and they have to recover, and then they lift a foot, and they go again. You got to stop. Okay? Especially if they're not on supplemental oxygen. Okay? The ones who are on supplemental oxygen, it's still hard. Okay? But they do a little bit faster. Your body's just not designed to operate at that altitude because of the lack of oxygen and the lack of air pressure. Okay? It's also why you can get hypothermia so easily up there. Okay? In the end, that's what usually gets people. Okay? Their body temperature just starts to drop, their metabolism isn't working properly, they get tired. And they're just like, I'm just gonna lay down here and take a nap. And they don't wake up. Okay? The air is too thin, there's just not enough oxygen. Okay? So we require certain conditions to live effectively. Okay? And that means we have to be down in the troposphere where we have those kinds of gases. Now, that doesn't mean the other parts of the atmosphere aren't important for energy transfer. They are. There are some things we don't want to get through. Okay? We don't want ultraviolet rays to get through. They do, naturally, but a lot of them get blocked by what layer? What's the layer that blocks?
The stratosphere, or?
It's kind of above the stratosphere / in the stratosphere, but it's a certain gas, starts with O.
The ozone layer?
The ozone layer. Yeah, so it's up in there. The ozone layer, okay, consists of ozone, which is 3 oxygen atoms bonded together, okay, and that blocks harmful ultraviolet radiation, okay. There used to be big holes in it, okay. They're getting smaller now because we understand what caused them, okay. We don't use those chemicals anymore, but there are still things that can affect it, okay. If stuff gets through there, then it's very harmful to us. Okay, so it's present there, okay, and the upper atmosphere part, that's where you're going to see like the aurora borealis, because you're going to be getting up into the magnetic field, okay, where that also protects us from things like gamma rays and x-rays and things that would literally fry us if they came through. Okay, so all of that stuff is important for keeping certain types of energy out and allowing certain kinds of energy in. Visible light and infrared, that's all good, that gets through. Okay, now, some of that infrared, the heat that comes in, it hits the Earth's surface and it bounces off. Okay, so it doesn't change the temperature of the Earth. What can it hit on its way back out? I'm sure you've heard this before. Something that traps energy that's in our atmosphere. It's the something effect. The greenhouse effect. There are greenhouse gases, and they're there. They're part of the atmosphere. Okay, but they're also an important part of retaining thermal energy. If the Earth didn't have any greenhouse effect, it would be a frozen ball. Okay, case in point, Mars. Mars has very little greenhouse effect, so it's a frozen ball. Okay, Venus, on the other hand, has way too much. Okay, like a horrible greenhouse effect that makes the surface of the planet hotter than the self-cleaning cycle on your oven. Okay, so we're kind of, the Goldilocks zone. We're right in, the happy place, okay, where it's just right. But obviously, if we continue to put more and more greenhouse gases into the atmosphere, then the effect will be amplified, okay, and it'll cause more heating of the Earth. Okay, but it's an important part of maintaining the right amount of energy, okay, thermal energy on the Earth to make it good. All right, so I'm not worried about you knowing the layers of the atmosphere. Okay, I don't care. I'm not going to ask you about the troposphere or the stratosphere. I want you to understand that the atmosphere is important for capturing, transferring thermal energy. It is the most important of the 3 parts. Okay, the greenhouse effect, certainly that's an important part of it. Okay,
Capturing and transferring what? Like
thermal energy. Okay,
Which source is that?
so which?
Which layer is that?
I'm not worried about the layers. You don't need to know the layers. I'm just saying the atmosphere in general is important for this. Okay, and it's obviously, because it's a gas, very fluid, so it can flow with the second law of thermodynamics. All right, so the atmosphere plays a critical role, okay, in maintaining the Earth's temperature, which we've kind of talked about. We got the greenhouse effect, things like that. Okay, much of the incoming solar radiation actually just bounces off the Earth's surface. Okay, maybe you were in like the 4th or 5th grade, okay, and you were learning about the planets, and then maybe your science teacher told you, planets are like big mirrors, and that's why we can see them. They reflect light back to Earth, and that's why we can see them. Planets are like big mirrors. They actually do reflect a lot of the light that comes in. Okay, Earth included. The thing that determines how much light gets reflected is this. Albedo. Very, very important term. Okay, albedo is a term that describes how reflective a certain object or area is. The higher the albedo, the more reflective that surface is. Okay? The lower the albedo, the more absorptive that area is. Let me ask you this. We get a big snow, the snow plows come out and they throw a bunch of sand on the road. Okay? Obviously, one of the functions of that sand is for traction, but it serves another purpose. What does it do to the color of the snow?
Changes it slightly.
Yeah, makes it lighter or darker?
I would say darker.
Definitely darker. Okay, it's brown. Snow is white. Okay, well, white is the most reflective color there is. Okay, if something is white, it is reflecting all of the colors to you. Okay, all of the light that comes in is being reflected off. So when we throw sand on the road, not only does it give us additional traction, but it also lowers the albedo of that area, meaning more solar energy will be absorbed by that snow that is now dirty. What will that make it do? Melt. Yeah, if it absorbs more energy, it's going to get warmer, right? If I had, let's say, two objects, let's say two cars in the parking lot, okay? It's out on a sunny day in June. One's black, one's white, okay? They've been out there all day. You come out after school and you touch them both. Which one can you keep your hand on for longer?
The white.
The white car, doesn't it reflects more of the incoming solar radiation. The black car, you'll hardly be able to keep your hand on it. Okay? It's also why black interiors in cars get so hot. Okay? I remember as a kid we had this old 1968 Ford Galaxy with black vinyl seats. I mean, you could not get in that car wearing shorts on a hot summer day. You would literally burn your skin. It would like burn onto the seats. They were so hot. Okay? Because black absorbs lots and lots of energy because it's dark. Okay? So the darker something is, the more energy it will absorb and the more its temperature will increase. Okay? Lighter colors don't absorb as much energy. Okay? Does that sort of make sense? Okay. So, albedo is important. Okay? If we compare, let's say we're just looking at like Okotoks right now. Okay? It's wintertime in Okotoks. What's the ground covered in?
Snow.
Snow. Snow is white. Okay? What's happening to the puny amount of solar energy that's coming in right now? It's getting reflected. 85 to 90% of it just bounces off the snow, okay, and off it goes, right? But as soon as that snow starts to melt even a little bit, it's not quite as bright white, okay? It accelerates the rate at which it snows. Okay? They've actually got a big concern right now for a lot of the glaciers in the Rockies because all the forest fires have resulted in a lot of ash falling onto those glaciers, which are normally pristine white. But with all that ash on them, they're darker. Is that going to make them melt faster?
Yeah.
Absolutely. Okay? So, 85 to 90% in the winter, okay, of the light coming in, the solar energy, thermal energy from the sun just bounces right off. Okay? That's why it gets so cold here in the wintertime. We're getting so little sun. The sun is not very intense because we're tilted away. And the ground's covered in white stuff that reflects it all away. Okay? I mean, I don't know if you've ever noticed this, but if you look, like if you've shoveled your driveway, the snow next to your driveway melts faster than the snow in your yard. Okay? The reason for that is it's next to something dark. Okay? That stuff heats up your driveway, heats up faster. Okay? It's also why we want our roads to be dark in color. If they're dark in color, they'll warm up faster, and the ice and snow will melt off of them more quickly. Okay? If you go to other places in the world, like say California, they don't even use asphalt in a lot of places. They use concrete instead. Because asphalt's black. And in the hot California sun, it'll get so hot that it'll get soft. In fact, that happens here. You ever notice that at the intersections, there's like big grooves where all the cars sit? Okay? That's because in the summertime, the asphalt gets soft. And when there's lots of weight on it, like big trucks, it squishes down. Okay? So, lighter color. Okay? Concrete's harder, lighter in color. In Arizona, they have this race called, there's a lot of death today, death race, okay? And the death race is through Death Valley, okay? They do it in the summertime, just stupid, but that's what they do because some people really like a challenge. But the people running it, they have to run on the white line on the road. So when they're running, they're actually doing this. It's almost like they're running on a tightrope because if they run on the asphalt, their shoes will melt. This is fun for some people, okay? Okay? But they literally, the road gets so hot that the rubber on their shoes will melt. Okay? So they actually have to run on the white line because the white line doesn't get as hot. Okay? Higher the albedo, the more reflection there will be. Okay? So about 10 to 15% of the sunlight coming in would be absorbed, 85 to 90 would be reflected, and of course anything that's dark, if you got a rock sticking out that's dark in color, the snow around that's going to melt faster.
So is this also kind of in relation to why they fill in like cracks in the road with like a asphalt? Or I don't exactly know what the material is, but they fill in like cracks in the road because water gets in it and heats up, and it kind of like, I think it expands. Or
It's not the water heating up,
Yeah.
it's the water freezing.
yeah.
If the
that's
water
what it
gets
was.
inside the cracks and freezes,
Yeah.
water expands when it
Yeah.
freezes, right? So yeah, they fill in the cracks because if water gets underneath and freezes, it'll heave, right?
Yeah.
Okay, in the summertime, it's the exact opposite, okay? You've got lots of, green grass and trees and things like that all doing their thing. Okay, if they're green, are they gonna absorb a lot of energy? Okay, they're gonna absorb it, but they're actually not just gonna absorb it, they're going to convert it. Okay, remember those big three we talked about right at the beginning? Absorb, reflect, convert. Albedo determines how much of that happens. Okay, if we're just talking about a big field of dark rocks, well, they're going to have a very low albedo. Okay, believe it or not, sand has a very low albedo. You ever walk on a beach on a hot sunny day? Okay? You can just about burn your feet. Okay, some places actually run like a soaker hose. Okay, from like the resort to the water because the sand gets so hot that people have to walk along the part that's wet. Okay, so things that are darker in color are going to absorb more energy because they have a lower albedo. They're going to get hot faster. Okay, if it's green and leafy, okay, it's a plant, then it's going to convert that solar energy into glucose using photosynthesis. So in the summertime, 70% gets absorbed, 20% gets reflected, okay, and you got about 10% getting reflected off of like the ocean and water bodies and things like that. Okay, so is it very different once you have different seasons? Okay, another reason why at the equator things are so different. There's never any snow covering anything, right? It's either dark in color or green and leafy, okay? It's really nothing else. Okay, is that making some sense? All right, so we got to know the three fates of light: absorb, reflect, convert, okay? Absorption and reflection are affected by this. Okay, here's how I'm going to ask you a question about this on your unit exam. I will take a satellite picture of some place on Earth. Okay? You don't even really have to know where it is. It's a color picture on the test. And I'm going to ask you, using this picture, tell me what's going to happen to the light that strikes this area and why. So if I show you the Columbia ice field, spoiler alert, I'm not, okay, but if I was to show you the Columbia ice field, okay, would you say that a lot of it is going to be absorbed or reflected? Okay, why?
It's a lighter color.
It's going to have a higher albedo, right? Okay, it's a light in color, so it's going to have a higher albedo, okay? And that means that the temperature is not going to go up very much because not a lot of energy is being absorbed, and there's obviously no green leafy things to do any photosynthesis or conversion of the light. Okay, so I would be looking for you to look at that picture and say, these are the three things that can happen to light. Here's how much of each one is happening and why. Okay, that sort of makes sense? Is that an application question? All right, so looking at this diagram here, okay, incoming solar radiation, okay, hits the Earth's surface, bounces off, and a lot of it gets backscattered.
Just go to the bathroom.
Yeah.
Thank you.
Okay, when stuff gets scattered, it means it just kind of goes everywhere. It's why the sky is blue. Okay? Some well-meaning soul somewhere along the way probably told you that the sky is blue because it reflects the ocean. The ocean is blue because it reflects the sky. Water is clear. Put it in a glass. Okay? It's not blue. The ocean is not blue. Okay? I don't know why they use the term deep blue sea. The ocean is clear. Water is clear. Okay? It only looks blue because the sky is blue. So it's actually backwards. Okay? And the reason the sky is blue is because the makeup of the gases in our atmosphere scatters blue light. So when the blue light hits our atmosphere, it just kind of goes everywhere. That particular wavelength of light is easily scattered by our atmosphere. Okay? Is the sky always blue?
No.
Okay. When the sun rises and sets, what color is the sky? Pink, orange, red, okay? When we had all those forest fires, what color was the sky? Orange. Okay, so if the sky is orange, what color is getting scattered? Orange. Okay, when the sun is low on the horizon, there's more particulates closer to the surface. Ash, okay, things like that, dust, all that kind of stuff is nearer to the surface. That particular stuff scatters longer wavelengths of light, orange, red, pink. Okay, that's why at sunrise and sunset, the sky is a different color. It's going through gases that are also full of ash, dust, pollution, okay, all of that kind of stuff, so it looks a little bit different. Does that sort of make sense? Okay, so scattering of the light is what causes the different colors of the sky. Okay, most of the time, it's blue light that's being scattered. Okay, why is it cooler generally on a cloudy day?
Because the sun's heat can't go straight from the sun into the Earth's atmosphere.
Okay, well, it's still going into the
Well,
atmosphere.
yeah, I guess. Well, it can't get to the troposphere layer without going through some clouds,
Right.
which absorb some energy. Or,
Does it absorb it?
Oh, reflect it.
Right, clouds are white, right? Or at least the tops of them are. Sometimes from our perspective, they look dark in color. That's just because they're really tall and not a lot of light is getting through them. So they appear darker in color, but the tops are white, okay? Highly reflective, okay, in the shade. Okay, making sense? So definitely that could be an application kind of question, okay? Thought here. Anyone ever made a quinsy? It's like an igloo, but not made with snow blocks. Just make a pile of snow and hollow it out. Okay? You can use them as an emergency shelter if you ever get stranded in the woods on a cold night, okay, and it's snowy. Not in the summer, it won't work. Can't make a pile of snow. Okay? But it works really well in the winter, okay, because once you crawl inside, what is the snow doing to all of your heat? Reflecting it back at you. Okay, and in addition to that, snow is an excellent insulator, right? Which we're going to talk about in a little while. Okay, but those are two reasons why getting inside a quinsy, okay, can keep you warm. Plus, it blocks you from the wind, which also helps. All right. So, gases present in the atmosphere help maintain the Earth's temperature. This is the greenhouse effect thing we were talking about before. Carbon dioxide, obviously the biggest of the greenhouse gases. Okay, chlorinated fluorocarbons, CFCs, okay, another type of one. That used to be in refrigerants, okay, it's one of the things that also destroy the ozone layer, okay, so now your refrigerator, air conditioners, and things like that use CFC-free refrigerants, which don't work nearly as well, but they're much better for the environment, okay. Methane, fart gas, okay, there's actually a big concern about it in places where there's a lot of methane being produced, like feedlots or things like that. Ozone, okay, nitrous oxide, all of those things allow the incoming radiation to go through, but when it hits the Earth, it is slightly altered by that reflection, okay, and when it comes back out, it bounces off, and it can go back and forth a whole bunch of times. Eventually, that just gives it more and more chances to be absorbed. The more chances it has to bounce back and forth, the greater the likelihood of it being absorbed and the temperature going up. Okay. All right, the hydrosphere. So all the water on the Earth. So quick review before we do the hydrosphere. Atmosphere is important because it's the most fluid, okay? Allows energy to transfer easily, okay? And it's nice and clear, so it allows the solar radiation to get all the way to the ground. Okay, so the hydrosphere is all the water above, on, or under the Earth's surface, okay? It could be water vapor, liquid water, or ice. Okay, it can also be groundwater, which is still liquid water, but obviously is under the ground. Okay, so if you have a well at home, okay, you are tapping what's called an aquifer, okay, that's groundwater. All right, actually much of our drinking water in Okotoks also comes from groundwater from wells. All right, so less than 0.1% of all the water evaporated from the surface of the Earth is returned to lakes, rivers, or streams, or seeps underground. The rest returns to the ocean or is frozen in the ice caps and glaciers. Okay, so if it was summertime and there was a puddle of water out here, okay, and it evaporated, 0.1% of that water would come back to that spot. Okay, it's going to be carried away, right? There's going to be circulation, air movement, it's going to go away. All right, so if we're looking at kind of a graph here, okay, So if we're looking at all water on Earth, 97% of the water on Earth is saline, that's salty, okay, ocean water basically. Okay? So only 3% of it is fresh. Who's got the most fresh water?
Isn't it Brazil?
Nope. Canada. We got the most fresh water, okay? You think of all the glaciers we have, okay? We have lots and lots of fresh water. All those lakes up in the north, tons and tons of fresh water, okay? So, of all the fresh water on Earth, 2/3 of it is frozen, okay? Well, or was at the time of this. That number is, of course, getting rapidly smaller, okay? But ice caps and glaciers represent a lot of the fresh water. Again, why Canada is so rich in terms of fresh water, okay? Groundwater, so wells and aquifers and things like that, 30%, okay? When we're talking about lakes and rivers, okay, that's like 0.3%, okay, of all of the fresh water on Earth, okay?
Well, we have to know the percentages.
Not at all. Please do not memorize the percentages. They are completely unimportant. Okay? All I'm doing here is illustrating how little of the water we have is actually fresh and how much of it gets stuck. Okay? You guys have learned about the water cycle like 4 times already. By the way, we're going over that one more time. Okay? The water cycle, this stuff gets pulled out of the water cycle. It doesn't come back until it melts and can run off, okay, and get back into the water cycle again. But it can be locked up in that for thousands of years. All right. Okay. See, Mary, I told you. Water cycle.
Sorry, what was the name of the last one?
What do you mean?
The lithosphere?
Yes, we haven't got to that yet. Okay, so you guys know the water cycle. You do need to still know the parts of the water cycle. But from our perspective, what's important about the water cycle is where the energy goes in and out. Believe it or not, the water cycle is one of the ways that huge amounts of thermal energy are carried from the equator to more northerly areas. Okay, the water cycle is a huge, huge part of thermal energy transfers. Okay, so just quick review of the water cycle. Liquid water can be turned into water vapor. We call that one of 2 things. It can be evaporation. That means that liquid water directly turns into a vapor. Okay? Or it can be transpiration. That means it came off of the leaf of a plant while the plant was carrying out photosynthesis. Believe it or not, that actually puts a huge amount of water into the Earth's atmosphere. Okay? Both of those processes require enormous amounts of energy. Okay, so to evaporate water, I mean, you've boiled water before. Does it take quite a while to get the water up to boiling?
Yeah.
It does, because it takes a huge amount of energy just to get the temperature to boiling, and then, can that water boil for a long time before it's all boiled off? It takes quite a while to boil off, even a liter of water, because it takes a huge amount of energy to turn liquid water into water vapor, this much. This number will be important later on. Okay, 2,260 joules per gram. Okay, so 1 gram of water is 1 milliliter. It's about the volume of a raisin. Okay, it takes 2,260 joules of energy to evaporate that much water. So, imagine a storm cloud that has moved in from somewhere else. It's full of water vapor. Does it represent a huge amount of energy? It does, okay? And when that water condenses back into a liquid, it gives off all of that energy. So if that water evaporated from the Pacific Ocean, okay, that took a lot of energy from that area. Then it's carried across the mountains to us, okay, and falls here. Well, we don't just get the water, we also get all the thermal energy it carried from that other place. Okay, so when we look at like a hurricane, okay, when a hurricane comes along, does it have a lot of energy? Do we see that in the destruction it wreaks? Yeah, okay, well, that's still the mechanical energy that's happening, all the wind and everything, but that energy came from all the water being evaporated in another place. Okay, the energy isn't just free, okay, it's coming from somewhere, and it's all from the water cycle. Okay, so evaporation and transpiration are energy in. Okay, there's going to be transport, wind usually. Okay, transport of what we call latent, that looks like hoot. It's supposed to be heat. I'm going to rewrite that because my handwriting is so awful. That's only marginally better. Heat, okay. So latent heat, okay? Latent heat is the energy stored in water because of its state. Ice has no latent heat, okay? It can't turn into anything else. Liquid water has some latent heat because it could freeze into ice, which is a lower energy state, okay? Steam, water vapor, has the most latent heat because it can condense and freeze, okay? All right, so energy goes in when water evaporates and turns into a vapor. It's transported in storms by wind as latent heat. And then here, the energy is released. Okay, when precipitation happens, the energy is released. The condensation process is actually the part that releases the energy. Okay, so the snow and ice that's stored in the glaciers, it doesn't have very much thermal energy. Does it still have some energy though? Yeah, because when it melts, it's going to, if it's on the top of a mountain, it's going to run downhill. Okay, we call that runoff. Okay, surface runoff. Okay. Is it converting potential energy into kinetic at that point? Okay, do we use that energy? Well, in Alberta we don't have very many of these, but hydroelectric dams sure do. Okay, that's still some of the energy, okay, is essentially stored here that came from here. Okay, we're talking about huge amounts of energy involved in the water cycle. Okay, we don't always think about it because we don't see it all together. Right? But there's a lot of energy involved in different parts of the water cycle. Okay, so you do still need to know the parts of the water cycle, but most importantly, you need to know where the energy goes in and where it comes out. Okay. Okay, questions on that? Okay, we already talked about this part, so we'll skip this part because we already talked about it. Okay, lithosphere. So now we're talking about all the solid, rocky, sandy, soil-like parts of the Earth. Okay, so in terms of energy, the lithosphere has basically no role in the transfer of energy. It does have a big role in the absorption and conversion and reflection of energy because it's the surface of the Earth that has the albedo we were talking about before. Okay, all parts of the Earth have a different albedo. Okay, if we're talking about a glacier, very high. If we're talking about the desert, very low. Okay, everyone follow there? Okay, so that's the role of the lithosphere. The lithosphere, in terms of thermal energy, its role is to control absorption, well not control, affect absorption, reflection, and conversion. Okay? And the conversion part, well, that can only happen if the surface of the Earth is just right. That is covered in soil that can allow plants to grow. Okay, so the most important part, okay, of the lithosphere to living organisms is the soil. Now, technically, any loosened surface is soil. Okay, bare rock is not considered to be soil. Okay, but any loosened surface is considered to be soil. Okay? Are some soils better than others?
Yes.
Definitely. Okay, depending on how loose they are, it's easier for plants to get their roots into them. Some soils retain moisture very well, some retain it too well, some don't retain it at all, like sand. Okay, all of that stuff factors into how well can plants grow in this area. Okay, and again, the role that plants play is they can convert the solar energy into chemical energy, which starts all food chains. Okay. Okay, so soil's the topmost layer of the Earth's surface, obviously where plants grow, okay, and we're talking about just terrestrial stuff. Obviously there are aquatic plants like algae and things like that, okay? It's an ecosystem and it has both biotic, living, and abiotic, non-living components, inorganic chemicals, air, water, decaying material, and living organisms. The lesson here, don't eat dirt. Okay, it's gross and it's dirty by its very nature. Okay? Nothing is dirtier than dirt itself. Right? And it's full of living organisms, like bacteria that could possibly make you sick, and bugs. Don't eat dirt. As a kid, you may have eaten dirt. You know better now. Okay? All right. Now, anyone ever dig a hole?
Yes.
Okay. What do you notice when you dig a hole? Okay, maybe there's worms, tree roots, plants. What else? Is the soil the same all the way down the hole?
No.
It gets what?
Darker.
Darker?
Wood.
Does it change its consistency?
It's
Yes.
more moist, right?
It can, depending on where you are. Sometimes if you're in a desert, digging a hole isn't going to get you to moist soil.
Often a lot of clay.
Okay, so you got your topsoil, okay? That's the part that's easy to dig through. And then you got underneath that clay. Clay is not as easy to dig through. It's very sticky, okay? And it holds onto moisture very, very well. Okay? If you kept digging, eventually you would hit,
Bedrock.
yeah, you'd hit rocks. In Okotoks, you hit the rocks very quick. Okay? The soil here is, in a lot of places, not very deep. Okay? When I used to live on the other side of town, we had to put up our fence, and when we went to dig the post holes, the bobcat could only go down this far before it hit the sandstone bedrock. Okay? It's pretty hard to keep a fence up when the hole is only that deep. Okay? So some soils are deeper, thicker, made of different materials, okay, than others. Why is the clay always under the topsoil? Maybe even if you had a sandbox. If you had a sandbox and you like dug down through the sand, there was clay underneath that.
Because I'm guessing the topsoil compresses it.
Well, topsoil does compress it, but I built the sandbox for my kids when they were little. I did not put any clay in it. None. But 5 years later, there was clay underneath the soil. How does it get
Moisture.
there? That helps.
I was gonna say moisture gets trapped.
Yeah. It's not just that moisture gets trapped, it's that moisture helps the clay get there. Okay? If you had a sandbox, sand is very gritty, right? You can put it between your fingers and you can feel the grit, right? There's big grains of sand. Clay, if you put it between your fingers, feels like flour. It's very, very fine, which means it's basically just dust. Dust that settles on top of the sand, on top of the soil. And then when it rains, those particles are smaller than the soil. So they get washed down underneath and they collect underneath. That's why clay always ends up underneath the topsoil. Okay? And it's why it retains moisture so well. Because all the particles are very small, they stick together and there's no spaces in between them. Okay? So there's no way air can get in there to evaporate the moisture. Does sand dry out really fast? Because the particles are very big. Spaces between them are very large and air can easily flow through there, so it dries out faster. Okay, so that's how clay gets to that point. But soil has these layers, okay, and the layers are important. Okay, so the layers are, okay, you have an O horizon. Okay, we don't always talk about the O horizon. We kind of say that it's part of the topsoil. Okay, so the A horizon includes the O horizon. It's the topsoil. Okay, that's the layer in which plants are going to grow, where the most biological activity is going to take place. all you really need to know about the soil layers is their letter and what they have. Okay, A horizon is the topsoil, organic material, okay, moisture, okay, things like that. Okay, so the A horizon, topsoil, mixture of decomposed rock, living organisms, and decaying organic material, so dead plants and animals. Okay, this is the part sometimes people have trouble getting their head around. Decomposed rock. Where does soil come from? It comes from the weathering of rocks. Okay, as rocks are exposed, soil slowly begins to build up. Okay, wind and water and things like that can slowly erode the rock in that area, and that will begin to collect and it will make soil. Okay? Soils are always like the bedrock. Okay? Sometimes we even call the bedrock parent material. Around here, our soils are very sandy. Okay? If you dig a hole around here, the soil is always very gritty because it's got a lot of sand in it. Because what's our bedrock here? What kind of rock do we have underneath everything?
Sandstone.
Sandstone. Okay? If sandstone is what we have, sandstone is what weathers, we're naturally going to have very sandy soil. If you're in an area where there's more limestone, then you're going to have soils that have finer particles and are naturally going to be darker in color. Okay? So your soil is kind of determined by what kind of rocks are in that area. Okay, so this would be a pretty typical prairie soil. We generally have pretty thick topsoil here, okay? Because every year when grasses die, okay, their leaf material just builds up and then new shoots grow out in the spring and you get this thick layer of thatch, which eventually breaks down and becomes more and more soil. Okay, so prairies, grasslands typically have pretty thick soil. All right, below that, okay, so here's the A horizon. Here's the B horizon, and then down below that would be our sandstone bedrock, parent material. Okay. All right, the B horizon has little or no organic material. It is mostly clay. Okay? You are going to find, tree roots and things like that going down far enough to get to the B horizon, sometimes even to the parent material, to the C horizon. But okay, there's not a lot of biological activity going on in these layers because there's not nearly as much oxygen. Okay, so B horizon, made mostly of clay, not an important biological part. Okay, so this soil right here, okay, there's the A horizon right there, okay, and the B horizon basically goes all the way to the bottom of the picture. Okay, would that be a very good soil to grow things in? Not for agriculture, but believe it or not, that's a tropical rainforest soil. Okay, in the tropical rainforest, there's almost no topsoil because it's always flooded, it always gets washed away, but clay can cement itself into one place. Rainforest plants actually get most of their water and nutrients directly out of the flood water they mostly grow out of. Okay? Soil is not a big factor for them in terms of nutrients. It's why slash and burn agriculture does so poorly. Okay? You slash down all the trees and burn them, and then you're trying to grow crops in this crappy soil. Okay? So that's why it doesn't work very well there. All right, and then the C horizon, okay, is composed mostly of parent material. Does that mean you can't have rocks further up?
No.
No, it doesn't. Okay, I mean, try and dig a hole around here. Okay, you're going to hit rocks all the time. Okay, rocks are going to be in every layer, but you're eventually going to get to a layer that is all rock, and then you're going to have real problems digging. Okay, short of explosives.
I mean, I'm sure if you whittled away at it from time to time, you'd be able to dig down.
Well, I threw a metal bar at it and tried to break it up, which, makes about that much progress.
It's
It's
still
progress. It was another inch of concrete that I got around the fence post. Okay, so again, that's a pretty typical soil profile for around here. Okay, you can see the soils are generally pretty light in color, okay, because they contain a lot of sand. Okay, I'm going to give you guys about a 4-minute break here, and then we'll pick up again with the energy stuff here. All right, so we're going to be going now like kind of full into the energy transfers and things like that. We've talked about albedo. We know the 3 fates of light that strike the Earth's surface are absorption, reflection, and conversion. Okay, but now we're going to kind of look at what happens once that energy is absorbed. Okay, where does it go? How does it get from one place to another? Okay, we know the second law of thermodynamics says it's going to go from hot to cold. That means naturally from the equator towards the poles, but it's a bit more complex than that. Okay, what are the processes that are going to move it? Okay, maybe you guys have heard of these 3 things. Here's another 3, right? And there's 3s and 3s and 3s. Conduction, convection, radiation, the 3 methods of heat transfer, probably grade 8 science. Okay, we're going to be talking about those here as well. Okay. All right, so obviously the biggest input that we're going to be talking about here is solar energy. It is far and away the main source of energy on Earth. Everything else is tiny by comparison. Okay, in terms of even like volcanism, geothermal, all of that kind of stuff. It's nothing compared to the amount of energy received from the sun. Okay. Okay, so within the atmosphere, the main method by which energy is transferred is convection. Okay, and it's why the atmosphere is the most important part of the Earth in terms of moving energy around. All right, convection is the movement of air, or any fluid for that matter, okay, because of differences in temperature. Hot air rises, cool air descends, okay, and it makes a cycle. That cycle is convection. Okay, we use that all the time, but it's a natural process that goes on the Earth. Okay, if there's more, heat energy, thermal energy at the equator, then air at the equator is going to move up, and cool air from further north is going to move down to replace it. Okay, and we're going to get a convection current going on. Right? What do we call moving air? Starts with W. Wind. Okay, this is what causes winds. Okay, is this natural movement of air because hot air is trying to go up and cold air is trying to come in to replace it. Okay, anyone ever been on a holiday near the ocean? Okay, did you notice that during the day the direction of the wind changes? Okay, in the morning you get what's called the sea breeze and the wind comes off the ocean. But at night, it goes the other way. It's called a land breeze at night. And it's basically related to a bunch of the things that we've just talked about. Okay? In the morning, okay, so you're going to have to suffer through my terrible drawings here. Here's the ocean. Those are waves. Okay? And here's the land. Okay, so in the morning, okay, is the land darker than the water? It is. It has a lower albedo, so it absorbs more solar energy, and its temperature goes up. Okay, the water is less absorptive, and it has a higher heat capacity, something we'll talk about later. Okay, so its temperature doesn't change nearly as much. So the air above the land gets warm and it rises. And the air above the ocean, which is cooler, rushes in to replace it. So you feel a sea breeze. Okay? And what's really going on is you're just getting a convection current, the movement of air because of differences in temperature. At night, the opposite is true. Undo. Whoa, not that far. Okay. This thing obviously doesn't know what I want. Let's go to the next slide. Oh man, how far back did we go here? I'm just gonna erase it because that'll be faster than what I thought was going to be faster. Okay, so at night, the land loses its energy faster than the ocean because it has a lower heat capacity, so it doesn't retain its heat nearly as well. So in the evening, the situation is reversed. The air over the ocean is warm and rises. Okay? The air over the land is cooler and goes this way, and you get a land breeze. Okay? But it's all related to just simply the movement of air. What part of your house is the coldest? Why? Because hot air rises. Okay? It's also why most of our houses here use a forced air furnace. Okay? Where are the heating registers on your main floor, not the basement? On the floor. Why aren't they in the ceiling?
Because then all the hot air will have risen.
Yeah, or it'll just stay there.
Yeah.
Right? If I'm blowing hot air out of the ceiling, I'm blowing it to where the air is already hot. It's just going to stay there. Okay? And you're going to get this weird temperature differential. Okay? For us, for heating, it makes more sense to have the ducts that the hot air comes out of to be on the floor where the coldest air is. Okay? And it's encountering that cold air and creating a convection current. In your house, you probably also have some registers on the wall. Okay? Little grates on the wall. Those are cold air returns. Okay? Naturally, okay, cold air is pulled through those and goes back to the furnace.
How come if hot air rises with altitude, it gets colder the higher you go?
And that has to do with how thin the air gets. So this is true, that whole altitude thing, there's 6 degrees, that's an average. Okay? But generally, as you go up to thinner air, its ability to retain heat decreases. So it's, yeah, it does seem counterintuitive. But trust me, yes, hot air does rise. Okay? It's why we get storms, but it's also why when it gets to a certain point, it condenses and falls back as rain. Okay, so hot air rises, cool air descends, okay, and we use that in our own homes to heat our homes. If you have a convection oven, okay, it has a little fan in it that makes sure that the air inside the oven is distributed evenly, so you don't have the top racks getting hotter than the bottom racks in the oven. Okay, things like that. We use all of that stuff, okay, to help kind of distribute energy within our homes more effectively. Okay? It's also the reason why this room has 0 temperature control. Okay? There's no ventilation in here. So throughout the day, it just gets hotter and hotter and hotter because there's nothing pulling the hot air. Okay? These things here on the ceiling that are not connected to anything that just look nice. Okay? They're supposed to pull the hot air as it rises away, and that little grate behind the red cart and that little grate behind my desk and that little one over there on the wall are supposed to be bringing in cooler air to regulate the temperature of the room. Okay, they're just using convection. Of course you want to put the parts that are going to pull hot air out of here on the ceiling. Now, how effective is that in the summertime for us in our regular homes where the vents are on the floor if we're trying to air condition the house? Now you got cold air coming out where the cold air already is. Okay? If you have a 2-story house, how can you make that more efficient? Which vents should you close?
Basement.
Basement and main floor. Have all the cold air come out on the second floor. That's where the hottest air is going to be. And cold air will naturally settle. Okay? You don't need to pump cold air onto the lower floors. They're naturally going to be cooler. Pump it all to the top floor where the hottest air is and let convection take care of the rest. It's way more efficient than just opening all of the vents in the house and having one floor be really cold and another floor not. Okay? You got to kind of use your knowledge. Was that an application that we just did there? Okay? These are the kind of things that are going to come up on the test. Okay? Using your knowledge of movement of air, convection, things like that to solve a problem. Okay? All right, so that's convection. Convection's huge. Convection causes winds, probably the most important heat transfer method that there is. Okay? The other two, okay, are radiation and conduction. We'll talk about those, okay, here in a minute. This is conduction right here. Conduction is heat transfer through a solid. Convection can only occur in fluids, so gases and liquids. Convection doesn't happen in a solid. Okay? In a solid, heat is transferred by conduction. Okay? Conduction means actual physical transfer of energy between particles. So the particles actually have to run into each other to transfer energy. Okay? So imagine you're like playing pool. Okay, there's a stationary ball and there's the cue ball. If you hit the cue ball and it hits the other ball, does it transfer energy to it?
Yes.
Okay, that's how conduction works. Okay, the particles get moving and they physically run into each other and transfer energy. Okay, so that's how energy can get from one end of a spoon to the other. So if you were, like, for whatever reason, stirring a pot of soup on the stove with a metal spoon, you shouldn't do that, by the way, okay, does the end of the spoon get hot?
Yes.
Okay, because the end of the spoon you have in the soup, in the hot liquid, okay, is getting hot. The particles there are moving faster and faster and faster, and they run into each other more often. And over the course of a very short amount of time, they will continue to move and transfer that all the way up the spoon, okay? And eventually the particles there will start moving faster. Okay? Does this work very well over long distances? It does not. Okay? It's fine for short distances, but this is why the lithosphere plays virtually no role in energy transfer. It's solid, and it can only transfer energy by particles running into each other. That doesn't work over big distances. Okay? Everybody all right with that idea? Okay? Radiation is energy transfer by waves. Okay? It is the way that energy gets to us from the sun. Okay? Radiation is not always a harmful thing. It's not what turns you into the Hulk when you get angry. Okay? Radiation is any energy transfer by waves. Okay? Right now, you are emitting radiation. It's thermal energy. That's why the room gets hotter when you're in it. Okay? You're always emitting thermal waves. It's what police infrared or night vision cameras can pick up. Okay? You guys ever seen that? Okay, right, like the criminals when they're running away, they're like this white blob. Okay, it's because they're emitting a whole bunch of thermal radiation, infrared radiation, that the FLIR camera, forward-looking infrared, can pick up. Okay, so it doesn't even matter if they're hiding in the bush. The bush is cold and they're hot and they're just like a sun inside of there, and it's just emitting a whole bunch of thermal energy that the camera can pick up. Okay, is that making some sense? So that's still waves. A fire emits radiation. Okay, it's thermal radiation. It's not harmful. It's not radioactive, but it's radiating heat. And in fact, you can sometimes see the effect of those waves. Okay, when you look through to the other side of the fire, you can sometimes see everything on the other side looks all wavy. Okay, the waves are transferring through the air. Okay. So within the hydrosphere, okay, we're looking at, so conduction isn't going to happen in the liquid, but convection is. Okay, so you'll have that convection, but you also have what goes on in the water cycle. Okay, so the hydrosphere, yes, there's some convection. That's what causes ocean currents. But the real role of the hydrosphere is the water cycle. Okay, and the energy transfers within it. Okay, so that's why we talked about it before. That is what we call latent heat. Okay, latent heat is thermal energy you can't feel, but is present. Okay, so water vapor has lots and lots of latent heat, but it doesn't feel hot necessarily. Okay, but when it condenses, it's going to release all of that latent heat back into the environment it condensed in. All right, so latent heat is a huge method of moving energy from one place to another in moisture-laden air masses. All right, so like a hurricane, okay? That is a huge moisture-laden air mass, and it is bringing tons of both thermal and even mechanical energy with it from the place it was born, out on the ocean where lots of water could evaporate because it was really hot. Okay, making sense? Okay, so the hydrosphere, its main role is to move energy through the water cycle and latent heat. The atmosphere's main role is to move it by convection. Okay, and then the lithosphere, its main role is the albedo part, absorbing energy. It determines how much energy is absorbed and reflected, and allowing for plants to grow, which allows the conversion. It has basically no role in energy transfer. Okay. Are there applications, like we already talked about, where your furnace grates are located for an application of convection? On a test, I would probably ask you something like this as an application of heat transfer. Maybe I would ask you how you could design something that could keep food cold on a hot, sunny day. Okay? So if I want to keep food cold, I want to minimize how much heat is absorbed. Okay, so what's a good bet for that?
Making it white.
Making it light in color, because that will prevent a lot of the radiation, okay, the radiant thermal energy, from being absorbed by that device. Okay? I also probably want to keep too much energy from convecting into it. If I just make it a solid wall, can energy get through that? Sure can. Okay? The windows are solid, can energy get through them? Yeah, okay, both by convection and by conduction. Okay, the walls in your house are solid, but they're filled with what?
Insulation.
Okay, you guys ever seen what that looks like?
Okay. Candy.
Yeah, it looks like cotton candy. Don't eat it. Okay, it's fiberglass. Right, it's very, very bad for you. Don't eat it. Okay, but here's how it works. It prevents both. Oh no. Oh no. Oh, now it's going really wonky. All right, so here's your wall. If your wall doesn't have any insulation in it, okay, this is outside, where it's cold, and this is inside, where it's warm. Okay, so the cold air here, okay, hits the outside of the wall, and it's going to make the air inside the wall colder. Agreed? Okay, but the air on this side is next to the warm inside of your house. So what happens is the warm air rises, the cold air from outside moves over to replace it, okay, and you get a convection current going on inside the wall of your house. It's going to very rapidly move the energy right out of your house. Okay, that's why we fill them with insulation. Here's what insulation does. Okay, insulation is basically just a rat's nest, okay, of interlocking fiberglass fibers. Okay, what's trapped in between all the fibers?
Heat.
Sort of. Air. The air's trapped. Can it circulate?
No.
So we prevent convection, okay, by not allowing the air to move. Insulation prevents the movement of air. Okay. Also, now the inside wall and the outside wall are not connected either. Okay. You'll be able, if it's really cold, you can tell where the studs in your wall are. Okay, those are the boards that hold up your house. Okay, just move your hand along the wall. If it's minus 30 outside, you'll be able to feel where the studs are, because they'll be colder. Because energy will conduct through that solid material to the outside. That's why we don't make our walls out of one layer of solid material. Okay? They would very easily move energy by conduction through. Okay? If we fill them up with glass fibers, well, glass is a very poor conductor of heat. And it's unlikely that any one glass fiber is actually going to be touching the wall on the outside and the wall on the inside. They're just a tangled mess. Okay? That sort of makes sense? Does styrofoam do the same thing?
Yes.
Yeah. Okay? Styrofoam is just foam, but inside that foam are tons of air pockets. Right? Those air pockets are tiny, and the air can't then circulate. So fiberglass and styrofoam insulate in the same ways. They prevent circulation of air, so they prevent convection, and because there's air pockets in the middle, they also prevent conduction, because conduction can't happen through a gas. Everyone okay with that? Conduction only happens through a solid. Right? We do the same thing if you have like an insulated mug. Okay? These have two layers. There's an outside layer and then an inner vessel. Okay? In lots of the thermos ones, actually, there's a vacuum. They actually suck all the air out between the two layers. Does that prevent convection?
Yes.
Yeah, there's no air, there's nothing to move. A vacuum is a great insulator. Okay, there's nothing to move, nothing's getting through there. And if it's a vacuum, no conduction can happen. Okay, but I tell you what, I can feel down here, the cup is cold here. But up here, where the two layers come together and they're welded together, it's warm up there. Okay, there's where the insulation breaks down. Plus on these Yetis, they got a clear lid, which is a real design flaw in terms of keeping the heat in. Okay, is that sort of making sense? Okay, so that's how I would maybe ask you. I would ask you an application question about the 3 methods of heat transfer. Okay, when we talked about the quinsy this morning, okay, when snow falls, okay, and you make a pile of it, do the snowflakes interlock? Are there air spaces between them?
Yes.
Can the air move? Snow's a great insulator. It's just like fiberglass. Okay, it prevents the movement of air, and it's white, so it's highly reflective. Okay, it prevents convection, it prevents conduction, it prevents radiation. Okay, it's a great insulator, other than the fact it has to be below 0 for snow to be there. Okay, but other than that, it's really good. Okay, I used to do this with my biology students back when I taught in Saskatchewan, and we would go on the coldest day. I would make them go outside and build quinsies. Okay, you would be amazed how fast people can pile up snow if they think it's going to be warm inside when it's freezing outside. Okay, so they'd build these big piles of snow in the middle of the football field. Okay, they'd hollow them out, and you get 2 or 3 people in there, and instead of being minus 30, minus 40, it's like minus 2. Some of them even got above freezing and start to drip on them. Okay, especially because they were all hot from doing all this shoveling. Okay, and so we would get it nice and warm in there. Okay, it's a great way to keep yourself warm. Okay, so the 3 fates of solar energy, make sure you have those down. Okay, reflection, there's no energy change. It's determined by albedo. Albedo is very high. Okay, absorption, energy is gained, temperature increases, also affected by albedo. Low albedo, high absorption. Okay, and then conversion or usage by photosynthesis. Okay, and that is converted from light to chemical energy by plants.